Hello everyone, in this video we are going to look at the next type of chemical calculation in Unit 3, and this type of calculation is called reacting volumes. It's very similar to excess but also brings in some of our molar volume knowledge as well, but I think out of the three types that we have covered so far, including this one, this is probably the most straightforward. So it's an important thing to remember that there is a correlation between the number of moles and volume. We know that 1 mole occupies a volume of 24 litres. The larger the number of the moles, the larger the volume, and vice versa. So that means if 1 mole of a gas produces 1 mole of another gas, then 1 litre of that gas would produce 1 litre of the product gas. And using these volumes in place of moles is how we solve reacting volumes questions. So if we had the production of ammonia by the Haber process, which is our reaction right here, we have N2 plus 3H2 gives 2NH3. In other words, 1 mole of nitrogen gas reacts with 3 moles of hydrogen gas to give 2 moles of ammonium gas. That means that since we have a 1 mole to 3 mole to 2 mole ratio, if we had 1 litre of nitrogen, that would react with 3 litres of hydrogen and produce 2 litres of ammonia. Or if we had 100 centimetres cubed of nitrogen, that would react with 300 centimetres cubed of hydrogen to produce 200 centimetres cubed of ammonia. So as long as we have the mole ratio, we can then scale our volume using that mole ratio. Let's try an example. So in the reaction below, 1 litre of nitrogen was reacted with 4 litres of hydrogen. What was the volume of ammonia produced? Well, step 1 is to find out which reactant is in excess. Because remember, if we have to identify the volume of ammonia produced, that's the product, then we're going to want to use the mole ratio of the limiting reactant and not the one in excess. So let's have a look at our mole ratio. We have 1 litre of nitrogen goes to 3 litres of hydrogen, reacts with 3 litres of hydrogen to produce 2 litres of ammonia. So if we only require in a 1 to 3 mole ratio 1 litre of nitrogen, we'll require 3 litres of hydrogen. That means that we have 1 litre of hydrogen extra. So hydrogen is in excess. And how we got that was we just looked at the equation here. We saw that 1 mole of nitrogen gas reacts with 3 moles of hydrogen gas. So 1 litre of nitrogen gas will react with 3 litres of hydrogen. In the question, we are given 4 litres, which means we will have 1 litre left over. So hydrogen is in excess. We are going to put a big cross through that and not use that. Our mole ratio that we're going to use to calculate our product is going to be our nitrogen to ammonia. So that's our 1 to 2 mole ratio. Okay, so what you can actually do is in this situation, I've just put it underneath, but if I'm writing this out on paper, I will usually put a big XS through the reactant in excess so that I remember to ignore that reactant. So here we have 1 mole of nitrogen gas produces 2 moles of ammonia gas. We have 1 litre of nitrogen, so that will produce 2 litres of ammonia. Hopefully you will see why it's very important to calculate which reactant is in excess, because had we used the 3 to 2 mole ratio for hydrogen and ammonia, then we would have got the answer wrong. It wouldn't have been 2 litres that came out. So it's very important, first of all, to determine which of your reactants are in excess and then use the other reactant, in other words, the limiting reactant, to calculate how much product is going to be produced. Now, there is another step to these questions, and the question can ask for the resulting gas mixture, which means not just the product, but any leftover reactants as well. So if that was asked in this case, then our answer would be, well, we have 1 litre of unreacted hydrogen from the beginning, and our product obviously is 2 litres of ammonia. So that's what we would write had the question asked for the resulting gas mixture instead of just the product. Okay, example 2. In a reaction, 120 centimetres cubed of ethane is completely burned in 550 centimetres cubed of oxygen. What is the volume and composition of the gas at the end of the experiment? So that's asking us, at the end of the experiment, what are we going to have and how much of it are we going to have? So let's first of all determine which reactant is in excess. We have a 1 mole of ethane reacts with 3.5 moles of oxygen to give us 2 moles of CO2. Now, we are not going to take into account the water molecules here because they are liquids and reacting volumes only deals with gases. So you can actually put a cross through your water. We are not interested in the water in this question at all. So, identifying which reactant is excess, how do we do that? Well, we take 120 centimetres cubed of ethane and then we multiply it by 3.5 and that will tell us how much oxygen we require. So if 1 mole of ethane reacts with 3.5 moles of oxygen, then 120 centimetres cubed of ethane will require to be reacted with 420 centimetres cubed of oxygen. In the question, it tells us that we have 550, which obviously is in excess of what we need, by 130 centimetres cubed. So at the end of this question, that's going to need to be included in our gas mixture. That has not reacted with the ethane. That oxygen gas is just sitting there in the product mixture. So we're going to have 130 centimetres cubed of oxygen. Now that we know that the oxygen is the reactant in excess, then we can use the ethane and the carbon dioxide in a mole ratio to determine which the volume of the product produced. So step 2, if 1 mole of ethane, 120 centimetres cubed, produces 2 moles of CO2, then that's going to be 240 centimetres cubed. Step 3 is just to calculate how much gas would be left over. We already did that. So we had 550 centimetres cubed of oxygen. We only needed 420 to react with 120 centimetres cubed of ethane. So we have 130 centimetres cubed of unreacted oxygen. And our CO2 produced, we had 240 centimetres cubed. The total volume of gas at the end of the reaction would have been 370 centimetres cubed, but it is required for you to write down how much of each substance there is, the way that I've got it written here. So that is reactant volumes. There really isn't a lot of differences between the different questions. You're either asked to calculate the volume of the products produced or asked for the composition of the gas mixture at the end of the experiment. Either way, you're following the same steps. Step number 1 is always to find out which reactant is in excess. Step number 2 is to use the limiting reactant to calculate how much of the product is produced. And then lastly, if you're asked for the total volume of gas or the gas composition at the end, just make sure to include your unreacted gas. Whichever gas you have in excess at the start is going to be included in that gas mixture. Let's try some questions. Here they are. In a reaction, 20 centimetres cubed of butane is completely burned in 150 centimetres cubed of oxygen. What is the volume and composition of the gas present after the complete combustion of butane? 2. What volume of carbon dioxide in litres would be produced during the complete combustion of 1 litre of propane gas? Now, the second question does not have an equation that requires you to write and balance a combustion equation. Hopefully everyone can do that since it was in Unit 2 and we've practiced it a lot. Let's see the answer for question 1. So we start off with our balanced equation and we realise that we have a 1 to 6.5 to 4 ratio. Remember and cross out your water because it's a liquid, it's not a gas, so we don't involve it in this calculation. Then when we substitute in our numbers, we had 20 centimetres cubed of butane. Now, if 20 centimetres cubed reacts in a 1 to 6.5 ratio, then that means we only need 130 centimetres cubed of oxygen. We have 150, therefore that means our oxygen is in excess, and we have 20 centimetres cubed of oxygen left over. If we then use our butane to CO2 mole ratio, we have 1 to 4. That means the 20 centimetres cubed of butane is going to produce 80 centimetres cubed of CO2. So the gaseous products we have then are 80 centimetres cubed of CO2 and 20 centimetres cubed of unreacted O2. Question 2. Let's just go back and familiarise ourselves. What volume of carbon dioxide in litres will be produced during the complete combustion of 1 litre of propane gas? So again, you have to write your balanced equation here. It's not given for you. But once you have done that, you can figure out your mole ratio here. You have 1 litre of propane gas, so that's going to require 5 litres of oxygen to react with, but it's going to produce 3 litres of carbon dioxide. That is a more straightforward example than the one before, but the complicated part of that would be you having to write your own combustion equation and balance it correctly as well for that to work out. So hopefully this video has been useful. We will practice more examples of all of the calculations so far in our live meet tutorials, but if you have any questions, you know where to find us. Thank you for watching.